Crystal clear water discharging as springs from rock formations is the most striking evidence that water exists in the Earth's crust. This spring water was once rain or snow that at some earlier time disappeared into the subsurface environment in which groundwater occurs. At this location, a spring feeds a small stream. Chemical compounds carried by the groundwater have coated the stream bed. The water emerges from the ground through all of the seasons, through wet years and through drought years, decade after decade, through geologic time. Many small streams originating from groundwater contribute to the flow of large rivers. At this location in the Rocky Mountains, spring water feeds many small ponds. The water emerging from the ground contains iron compounds that stain the ground. Although groundwater generally is free of chemicals created by man, it has a variety of natural salts that give it a character of its own, a chemical character that differs from region to region. Almost all waters on or beneath the ground originate as rain or snow. On the ground surface, some of the water flows towards streams, lakes, or marshes. Some infiltrates below the ground surface to become soil water. When the soil is very wet, the water may move deep enough to feed the groundwater zone. Below the water table in the groundwater zone, water continually moves along flow paths from zones of high to lower fluid energy, some of it flowing into surface water bodies where part of it evaporates. This passage of water through the atmosphere, through rivers and lakes, and through the ground is known as the hydrologic cycle. Many groundwater zones can be detected only by the drilling of boreholes. This hole is being augured to a depth of 7 meters for installation of an observation well below the water table. There is no sign of water dripping from the augers. There is no free water on the clay soil samples taken from below the water table. This observation well will be lowered down the auger hole. The well screen will be placed a meter below the water table, where water will slowly seep through the screen into the well. In the well, the water will rise eventually to the level of the water table. When a shallow observation well is installed below the water table in clay deposits, the well will initially have no water. Gradually, water in the clay will seep into the well bore. And eventually, the water level in the well will have a level that is the same as that of the natural water table. Near the surface, the geologic material is dry in this deep excavation. At depth, it becomes increasingly moist. And at the water table, groundwater flows freely into the excavation. Gradually, the water table is being lowered because of seepage into the excavation. In non-arid climatic regions, periods of rain or snowmelt cause the water table to exist near ground surface. During dry periods, or when the soil is frozen, the water table declines to lower and lower levels as moisture is lost by evaporation, plant use, or flow towards other areas. When infiltration from rain or snow occurs once again, the water table returns to higher levels. The water table constantly changes its position through the seasons. To understand groundwater conditions, observation wells at different depths are needed, sometimes up to 10 or even more. Here there are 3 wells. Measurement in the shallowest well indicates that the water table is 1 meter below ground surface. The deepest well at this site is a flowing artesian well, which means that its water level is above the ground surface. Flowing artesian wells occur in many regions, another indication of the dynamic nature of groundwater systems. The casing of this artesian well was extended far above the ground for installation of an automatic water level recorder. The recorder monitors the changes in level of a floating device on the water surface. Observation wells with water level recorders now exist at thousands of locations throughout North America. To determine whether groundwater moves upward or downward near the water table zone, 2 or more wells are needed. The water level in the deeper well rises to a level much above that of the water table. The hydraulic energy of the deeper groundwater is highest. The direction of groundwater flow is upward. This is a discharge area. Water flows from zones of higher energy to zones of lower energy. In this different hydrologic setting, the water level in the deeper observation well is below the level in the water table well. The deeper water has less hydraulic energy. The direction of groundwater flow is therefore downward. This is a recharge area. In recharge areas, water is supplied to the groundwater zone by infiltration through the soil zone. In discharge areas, water is lost from the groundwater zone by upward migration through the soil zone. Groundwater travels from the recharge to discharge areas along short local flow paths where it is young, or along regional flow paths where it can reside for very long periods of time. From recharge to discharge area, groundwater is continually in motion. This well with clear artesian water is being sampled for a study of groundwater age. The carbon-14 age dating method is being used. Chemical compounds are added to the groundwater sample. The compounds react with the natural carbon in the groundwater to cause precipitation of white carbonate crystals. The carbonate crystals form gradually and slowly settle to the bottom of the sampling apparatus. The carbonate crystals are taken to the laboratory for radioactivity analysis. As groundwater travels along its flow paths, radioactive decay causes the carbon-14 content to decrease. This decrease is used to estimate how many thousands of years the water has existed below the water table. In this recharge area, the water table is more than 2 meters below ground surface. Each year, water flushes through the soil to the water table. Dark organic matter derived from vegetation accumulates in the soil, and at the same time, infiltration carries dissolved mineral matter downward to the groundwater zone. The groundwater, therefore, contains much more dissolved material than the rain or snow from which it is derived. This site is in a groundwater discharge area where the water table is shallow. Salts are brought to the water table by groundwater flow and are then carried upward into the soil by capillary movement. As the soil water is lost to the atmosphere by evaporation and plant use, the salts are left behind. Gradually, saline soil zones develop as the salts occupy an increasing portion of the pore space in the soil. Eventually, the salt may prevent the soil from supporting plant growth. Across the plains region of North America, salt from groundwater is damaging large areas of agricultural land. In some areas, geologic layering is an important factor in groundwater discharge. This escarpment is formed from stratified sedimentary rock, mostly shale. On the slopes, parallel to the geologic layers, shrubs and small trees seeking moisture grow along a layer of moist yellow clay. Because of joints in the weathered shale, groundwater moves rapidly downward until it encounters the soft, impervious yellow clay. The groundwater is diverted along the clay layer to the valley slope. Groundwater discharge is the main source of water for many ponds or marshes. It is the lifeblood of these ecological systems. This marsh is fed by a series of springs from which water upwells from an underlying aquifer. Water has been bubbling from the ground at this location for thousands of years. In the sandy center of the spring, the seepage produces a small area of quicksand. Good places to observe the effects of groundwater flow in sand can often be found along the bluffs of rivers or lakes. Sands or gravels deposited during the geologic past are often very permeable. Groundwater flow in these deposits is normally quite active. Although the flow of groundwater is not as erosive as that of most rivers, in its own slow way, it gradually dislodges sand grains and weakens the main body of the bluff. Over time, the effects can alter the shape of the landscape. At this riverbank location, groundwater has been continually a contributing cause of landslides or slumps. Year after year, the fallen debris is carried away by spring floods. The main zone of groundwater seepage is halfway down the slope. High groundwater pressure and the continual seepage from the bank cause earth movement that can develop into mud flows. Although groundwater plays an important role in alteration of the Earth's surface through landslides and its influence on river behavior, it is better known for the changes it makes below the Earth's surface. A group of cave explorers in the Rocky Mountains have set forth to examine caves that penetrate deep into the mountainside. At one time, flowing torrents of water from melting glaciers caused these rock tunnels to form. The cold, dilute water caused the limestone to dissolve. Small cracks became large openings, and the cave network spread. The torrents that formed the caves have gone. Now, slowly dripping groundwater forms delicate mineral formations on the ceiling and floor of the cave. The groundwater is now forming mineral matter in the cave rather than removing it. This is a part of the dynamic evolution of underground space in limestone. In contrast to increasingly polluted surface water, most groundwater is free from pollutants. It is available to those who have the ingenuity to find it and extract it. Drilling for water is becoming critically important in many parts of North America. Underground water supplies are called upon more and more to serve the needs of the modern economy. Groundwater provides more than 1/3 of the freshwater resources of North America. It supplies industry with water for processing, cleaning, and cooling systems. It provides clean, cool, unpolluted water to people in the cities. In many regions, groundwater has become the very life of a vast agricultural industry based on irrigation. Although groundwater occurs in nearly all types of geological deposits, only the very permeable materials can yield water to wells at large flow rates. These deposits are known as aquifers. In this quarry, we can see one type of aquifer material. Clean sand and gravel is porous and permeable, and where it occurs below the water table, can yield great quantities of groundwater. Some aquifers consist of numerous layers of sand and gravel. Others are more uniform, such as this sand deposit. Many different methods are used in the search for groundwater reservoirs or aquifers. Here they are using geophysical methods. Electrical currents are being passed through the ground to obtain an indication of aquifer occurrence. Silt and clay are the best conductors. The electrical current passes less readily through sand and gravel, even when it is saturated with groundwater. The measurements of voltage at electrodes pushed into the soil can provide information on aquifer size and depth. The most direct way of finding aquifers, however, is by drilling. As the drill bit penetrates deeper into the ground, the nature of the geologic materials becomes known. This drill rig uses the rotary method with mud circulation in the borehole. The circulating mud brings cuttings of the geologic materials from the bit to the surface, where samples can be taken. When an aquifer is encountered, The drill mud can be removed by circulation of air or water. As the mud is flushed from the system, water from the aquifer gradually becomes the discharge from the hole. A steady yield of clear water is confirming evidence that a groundwater reservoir has been located. When groundwater is pumped from wells, the water levels in the aquifer decline. In this example, the aquifer is near ground surface. Pumping causes drawdown cones to form in the water table surface. Too much pumping causes the water level to decline to the well screen, and the aquifer becomes overexploited. Excessive aquifer dewatering can often be avoided if wells are placed near rivers, streams, or lakes. Initial pumping causes rapid decline in the water table. Later, the drawdown cone spreads to the surface water body. The river or lake water is then drawn towards the well and continuously supplies most of the water pumped from the well. As the water passes through the aquifer, it is cleansed. Often all pollutants are removed. Groundwater resources are being carefully managed, often in ingenious ways. For example, in this area south of San Francisco, water from faraway mountains is brought by engineered hydraulic systems and used to replenish large natural underground reservoirs. From man-made ponds located at many strategic points in this urban area, the imported water seeps downward into the aquifer. They work to get it down quickly with the least loss by evaporation. After use, the pond bottoms are plowed so that sediment clogging will not cause excessive reduction in the infiltration rate. When aquifers are excessively pumped, the water table is lowered, causing shallow wells to go dry, shown here in black. As pumping continues, water levels decline further, and deeper wells go dry. As the groundwater pressure is reduced, layers of silt or clay in the aquifer system are compressed. This compression causes the land surface to subside. This has happened in many places, in California, Louisiana, Mexico, Italy. Here, for instance, in the south end of San Francisco Bay, the ocean level is now far above the ground floor of buildings. The ground floor of this building once looked out over the water. Now, after decades of land subsidence, the land area must be protected by a dike. The water can barely be seen from the second floor. In many parts of the world, groundwater in the form of natural steam emanates from the Earth's surface, providing evidence of hot zones deep beneath the land. In recent years, the heat energy in groundwater in these geothermal zones has been harnessed to produce electrical energy. Geothermal power plants at this site in Northern California produce enough electricity to supply a city of 1 million people. The energy in the form of steam is tapped by drilling boreholes deep into the hot, fractured bedrock. Dozens of boreholes are required to provide the necessary steam to the huge power generators. Today, geothermal zones are used for the production of electricity in more than 10 countries. As the United States and Canada endeavor to satisfy their ever-increasing power demands, more and more coal is used to produce electric power. Large areas of the Earth's surface are scheduled for strip mining. The coal mines are cut below the water table, and groundwater flows into the excavations. Gradually, the gentle seepage causes the water table to decline, and in the vicinity of the mine, wells go dry. In some areas, the effects on groundwater are slight. In other areas, the water level drawdown spreads far from the mine. In the eastern United States, groundwater flowing into coal mines undergoes chemical changes as it becomes aerated. As it picks up iron and sulfur and becomes acidic, the water becomes an environmental hazard. Each year, billions of liters of acid mine water drain from coal mines into streams and rivers. At thousands of locations, garbage is a source of pollutants that move down into groundwater zones. And man's activities are affecting groundwater resources in many other ways. Liquid industrial wastes charged with toxic compounds are being discharged into lagoons for storage or treatment. In proper geologic settings, lagoons are safe. Many lagoons, however, are leaky, feeding hazardous chemicals into the groundwater zone, chemicals which may migrate toward drinking water supplies. Unfortunately, once an aquifer is polluted, many decades or even centuries may pass before it once again produces clean, cool water. Protection of the quality of groundwater resources is a major challenge facing our industrialized society.